Hello all of you. Welcome to the 43rd lecture of the course on analysis and modeling in chemical engineering. In this lecture, we will revisit the Badger-McCabe method we discussed when we were discussing about evaporators long back in this course, and that was kind of an iterative method that we have developed based on the guesses of the temperatures and so on. We will discuss that method also in this course, in this class, but we will see that how we can use graph theory to justify that particular iterative scheme that we have developed. And then we will discuss the more general idea of tiering a graph that basically ensures the maximal reduction. In the last lecture, we also discussed one example where the proper choice of the variables, the given variables, made my life quite easy. We got rid of the cyclical net and things like that, and then the decomposition was quite straightforward. Now we extend that idea not only for the given variables, but the variables that we can guess in order to make the equations easier to solve or to develop an iterative scheme for solving the equation. So let us quickly recap the what we have discussed in the triple effect evaporators. So again, you can look at how we got these equations from looking at the discussion of evaporators in this course. But basically what is happening is we have essentially three effects here. Feed enters the first effect and fresh steam is also supplied to first effect if we have the forward feed. If we have the reverse feed, then the feed enters the last effect, but let us focus on the forward feed. And then the liquid gets evaporated inside the evaporator, and the vapor that leaves that evaporator, that vapor basically is used to heat the second effect, and the concentrated liquid leaving the first effect becomes the feed to the second effect. Similarly, the vapor leaving the second effect becomes the feed to the third effect, becomes the heating medium for the third effect, and the liquid leaving the second effect becomes the feed to the third effect, right. And based on that, we have got three energy balance equations for this system and three heat exchange equations. We also had solute balance equations like this, but then we have noted that since the solute mole fractions are not appearing in any other equations, we can take them separate, we can solve them after we have solved for the remaining variables, right. So we have chosen a particular choice of unknowns as L1, L2, T1, T2A, and for this case we will develop the Badger-McCabe method. So for this case, let us first begin with doing the occurrence matrix for this particular set of equations. So as we discussed in the last lecture, so we have 6 equations, 1 to 6, and for this case the unknowns are S, L1, L2, T1, T2, A. And as we can see that S is appearing in the first equation, L1 is also appearing in the first equation, T1 is also appearing in the first equation, L2 and T2 is not appearing, and A is not appearing. For the second equation, S is not appearing, but L1 is appearing, L2 is also appearing, T1 and T2 are both appearing in this equation. And then for third equation, again L1 and L2 are appearing, S is not appearing, and T1 is not appearing, but T2 is appearing in the third equation. For the fourth equation, S is appearing and T1 is appearing and A is appearing. For the fifth equation, L1 is appearing and T1 and T2 both are also appearing and area A is also appearing. And for the last equation, the L1 and L2 are appearing and then T2 and area are also appearing. So, this is the occurrence matrix for this case. Let us make a choice of the admissible output set. As we discussed in the last lecture, this is going to be along the diagonals. Of course, I can look at other permutations, but this is clearly one choice where we choose along the diagonals, where the first one I used to get S, second one I used to guess L1, third one I used to get L2, then the fourth one for T1, fifth one for T2 and last one for A. So, now we can do the Boolean matrix for this particular case, right. So, first I have to convert this occurrence matrix into the corresponding R, and we can do that by the method that we have discussed by looking at S is a input to which other vertices. That is one way of doing it. The other simple way of doing it is simply take a transpose of this matrix that also basically gives you the Boolean matrix. We will take a simple route. So, we take a transpose of this and the Boolean matrix therefore becomes these are the labels. So, first row is 1 1 1, that becomes a column here. Then second row is 3 4, that becomes column here. The third row is second, third and fifth, that becomes a column here. The fourth row is first, fourth and sixth, that also becomes a column here. Then fifth row is second, fourth, fifth, sixth, that also becomes a column here. And the last row is second, third, fifth, sixth, that also becomes a column here, right. So, we can use the alternate way as well, but this is a simpler way. We simply take a transpose of the occurrence matrix and that gives me the Boolean matrix. Now, we can do the graph. So, we have self loops, but anyway we are going to not worry about it later, but just for the sake of completeness, let me do the self loops corresponding to the diagonal terms. And then from 1 to 4, we can go in one step. Then from 2, I can go to 1, 2, 3, 5, 6. And from 3, we can go to 2, 3, 6. 3 to 3 is self loop. And from 4, we can go to 1, 2, 4, 5. Four to 4 is self loop. And from 5, we can go to 2, 3, 5, 6. And from 6, we can go to 4, 5, 6. and 6 to 6 is a self loop. And you see that the graph already looks quite complicated, and we can try to decompose it, but what you will find is that all the 6 equations pretty much has to be done simultaneously in this particular case. We do not find any simple reduction here. Even if we get rid of the self loops, which we should, we still have no columns containing all zeros, no rows containing all zeros. We have to go ahead and try to figure out the cyclical net of order 2 containing no ancestors or no descendants. And if we do this process, we will see that eventually we have to solve probably all the 6 equations simultaneously. So what we can do in this case, right? So in the method that we have described, what we have done is we have guessed the T1 and T2, and once we guess the T1 and T2, now we go to this last 3 equations, and instead of the area variable A, we introduce the variables A1, A2, A3, and we compute A1, A2, A3. Let me call these equations 4 star, 5 star, 6 star, just to make sure that these are not the same equations, right? And using this A1, A2, A3, we basically update the T1 and T2, and then we go back here until convergence, right? I am not writing down the formula how we did it. In fact, we redistributed temperature drop. That's not very important here. What we want to see is that whether that particular choice of guess variables made our life very, very easy, right? Or could there have been some other choice of guess variables, right? So let us go back and try to do the graph for this new Badger-McCabe method, right? This method that is the iterative method. And now the variables are changed because we have guessed T1 and T2. The new variables are S, L1, L2, A1, A2, and A3. Let us do the occurrence matrix for this particular case. So we have the equations. So clearly S is appearing in the first equation, and L1 is still appearing. T1, T2 is anyway guessed, so we don't care about that anymore, right? And the area values A1, A2, A3 are not appearing in this equation. So only S and L1 appears in the first equation. The second equation does not contain S, but it contains L1 and L2, and it doesn't contain A1, A2, A3. The third equation again contains L1 and L2, but doesn't contain A1, A2, A3. The fourth equation contains S and A1. The fifth equation contains L1 and A2. And the sixth equation contains L1, L2, and A3. And now again, we can choose admissible output set along the diagonals. These will give you self loops in the matrix. And again, we can do a Boolean matrix by essentially taking a transpose of this. So let us take a transpose here. And let us get rid of the self loops, because anyway we are going to delete for decomposition. So once we get rid of the self loops, we don't have this diagonal there. So I'm going to delete that from the graph. And now I am left with this. And now we can apply our standard decomposition scheme. And we see that in the R matrix, there are no columns containing all zeros. So the next step is to identify the rows containing all zeros, right? And in this case, the row 4, row 5, and row 6 contains all zeros. So we can solve them at the end. Solve 4, solve 5, solve 6 in any order. And then we can get rid of the rows and columns containing 4, 5, 6 vertex. And now we can see that in the remaining matrix 1, 2, 3, there are no columns containing all zeros, but the first row contains all zeros. So I can solve that equation just before the 4, 5, 6. I can do it second last. So we can solve 1. And then finally, I am left with 2 and 3, and that is basically the reduced matrix looks like that. If I take a square of this, if I take a square of this as expected, I am going to get diagonal ones, and that means that we have a cyclical net of order 2 between 2 and 3. So we solve 2, 3 simultaneously in the first step and 1 after this, right? And then now you can see this is pretty much what we did. So we can solve equation 2 and 3 simultaneously for 2 and 3, that is L1 and L2. Keep in mind that we have assigned L1, L2 as the admissible output of 2 and 3. So then once we have got this, I can solve S from the first equation, and once we have got S, L1, L2, I can get A1, A2, A3 from the remaining equation, pretty much what we have done in the Badger-McCabe method, right? Now the question is that, was that a good choice, right? How do we know? It would have been a good choice if it gives you a large reduction in the solution scheme. As we can see, the original graph looked something like this, and we had to solve 6 by 6 matrix, and now the maximal cyclical net possible is only of order 2. So we have to only solve a 2 by 2 matrix. Once we have done that, then all the other steps are quite straightforward, right? Now the downside of this is that we have to do this now iteratively, right? So although we have reduced the complexity of the graph, we have introduced an iterative scheme that has to be done, right? So provided that it just does converge within few iterations, whatever benefit we are getting from decomposing this particular graph by guessing the variables, that benefit can be realized, right? So this kind of procedure where we choose some of the variables as the guess variable, resulting in the decomposition of or reduction of the flow sheet, this particular method is called the tiering method, right? So going back here, what our method actually amounts to is basically reducing the complexity of this particular graph by basically getting rid of the all the variables like T1 and T2, right? And you can see that the choice of T1 and T2 is somewhat straightforward, because T1 and T2 are appearing in large number of rows in my matrix, right? Of course, the overall temperature drop was given, and that made our life easier in developing the scheme. But what is also known is T1 and T2 is appearing in basically 4 elements if I look at the columns of T1 and T2. As opposed to that, S is appearing only twice, A is appearing thrice, L2 is also appearing thrice. If you think about it, L1 could have been a guess variable because L1 is appearing 5 times, right, in 5 equations, right, in the first, second, third, fifth and sixth. So, L1 could have been a guess variable, but then choosing T1 and T2 happened to be a better choice because we could develop the update scheme based on the temperature drop, right. But whatever we have chosen is basically able to give the reduction in the graph because it is appearing in many equations. So, equations becomes easier to solve. So, in general, the graph theory can help us identify which edges can be torn from the graph in order to basically develop an iterative scheme that can reduce the complexity of the problem. And we can basically judge or look at the efficiency of different iterative schemes by analyzing them as graphs, right. So, that is the whole idea that we have here. So, with that, I am going to conclude this lecture, but there is few other points that also has to be considered here, that how do we choose the tiered stream. One thing is very clear, that we want to get the maximal reduction in the complexity of the structure. But what is also important is that it should have a minimum sensitivity on the result. If, for example, you choose a guess variable for which the results are highly sensitive to that variable, in that case, the iterative scheme is going to be somewhat unstable. If just by changing this value of this guess little bit, if this scheme gives me a very drastically different result, that means high sensitivity, in that case we have a problem. So, we have to make sure that whatever variable I am choosing as the guess variable, it does not drastically affect the result, right. In fact, for the evaporator problem, our life was easier because we knew the upper bound of temperature and the lower bound of temperature, and therefore, the T1 and T2 must be between this range. So, we already had a choice. In fact, I could have made a simple choice by choosing T1 and T2 something like 1/3 between Ts and T3 and T2 2/3 between Ts and T3, right. So, we can ideally linearly interpolate between Ts and T3 to guess the value of T1 and T2, and provided that we know these two bounds, my final results are not going to be that sensitive to T1 and T2, right. One of the reasons why we did not choose this L1 as the guess variable, although it was appearing in the 5 equation, is that we were not aware of that kind of bound possibly for this case, right. So, for T1 and T2, these bounds were there, and therefore, it is kind of seen that probably the sensitivity of temperature is not as high as the sensitivity towards this flow rate L1, although this is quite subjective and we have to see the actual sensitivity by performing simulations. And finally, the requirement is that whatever iterative scheme we come up with, it should show nice convergence, right. What is the iterative scheme good for if it is not converging properly, right. So, in the end, apart from the consideration of the reduction in the complexity of a structure, we also need to look at the sensitivity and the convergence of the iterative scheme to indeed ensure ourselves that this iterative scheme will perform better than, let us say, solving all the equations simultaneously, right. Again, for this particular example, we only had 6 by 6 matrix. So, the benefit from doing this iterative scheme may not be as high, since we could have done a Newton-Raphson for this, and as we have demonstrated, it works quite well. But as we extend this idea to a much bigger system, you can see let's say for a flow sheet containing thousands of units, if we can nicely identify the tier streams, that can really reduce the complexity of the curve by very large extent, right? So with that idea, I want to pretty much conclude the discussion on graph theory for nonlinear systems. In the next lecture, we will see how graph theory can be applied to other contexts. We will take example of reaction mechanisms and show how the graph theory works in that case. So with that, I stop here. Thank you so much.